about in astronomy, that's the speed of light. Like, for instance, you know, I turn on the light switch, and you just think, oh, I think electricity is awesome, by the way, but you just think that basically when the electrons around the gas molecules get excited, they emit light, and you just think it just gets here right like that. But actually, there's this concept called a light year, where if you place that thing 1 light year from us, it takes 1 year for that light to reach us. So light takes a certain amount of time to happen. And I liken that to chemical reactions, because like chemical reactions, you mix the reactants, they go to form products. How long does it take? I don't know. It goes like that. But actually, and in tomorrow's lab, you're going to see how long it takes. Okay? It takes a certain amount of time. So in chemistry or physical science, we have this thing called reaction kinetics. And reaction kinetics look at not only how fast a reaction occurs, but we're going to actually talk about something called mechanisms. We're going to talk about reaction mechanisms, and that talks about the pathways that are happening, what I call behind the scenes. So reaction kinetics talks about how a reaction rate and also kind of what we call kind of the mechanisms behind the scenes. So reaction kinetics are awesome. They're things that we just generally take for granted. Oh, I know that if I mix A and B, it's going to go to form C. Duh, right? Well, how fast how long does it take for that to happen? And what's happening behind the scenes? So it's reaction kinetics. So generically, we know that we put the reactants on the left and the products on the right. Okay, reactants go to form products. The convention coming up here on a few slides, I bet you're fine with this, is we put an R for reactants, okay, goes to form products, right? Okay. So how long does it take? Well, basically we could do two different things. We could look at the product, I'll put a plus mark over here, building up, okay? We could say, well, P, I can see that we get 1 mole per liter of product, or we get 2 mole of liter per product, or 2 moles of product per liter in this amount of time, okay? We could look at the product forming, or quite frankly, we could look at the reactant going away. Okay, so we could track either one of those. So on the next slide it says, well, I'll just wait for the next slide. So again, we could look at the reactant. I put a negative sign here, decreasing, or the product, I put a plus sign here, increasing. We could track either one. Now, one thing that's universal is a reaction rate over time will slow down. And when we look at factors affecting reaction rate, to me, the biggest thing is, an hour down the road, do you have less reactants? Yeah. Okay, so is it going to proceed to form products at the same speed? No, it slows the heck down. Okay, so as time increases, I'm going to put up arrow here, as time increases, reaction rates decrease. This is an inverse relationship. Time increases, reaction rates decrease. So we can show that, by this proportional to the inverse. Okay, so that infinity sign with a byte taken out is proportional. We show that we have an inverse relationship by showing time is inversely proportional to rate. As time increases, rate goes down. We could also kind of show the relationship like this inverse relationship here. Rate will decrease as time increases. Now, I was thinking about that. Can you say time decreases? I usually think chronologically, time is increasing. Literally, we're allowing the experiment to proceed. It's so cool. Okay, so the R stands for reactants, the P stands for products. Now, what do those brackets mean? We looked at this before, square brackets?
Molarity.
Molarity, exactly. So here in Chem 2, like for the rest of the semester, I'm counting on anytime you see something in brackets, you think molarity. So this is just kind of, I meant to print this out. So if you want to put a little star here, you're going to be referring to this on these other slides. So let's just say simply a reactant goes to form products over time. So at time 0, doesn't this make sense? At time 0, all we have are reactants, no products. We're going to let her cut her loose, and looks like we're going in 5-second intervals at times equal to 5.0 seconds. Notice what has happened to the reactants. The molar concentration of reactant. It decreased. What has happened to the molar concentration of the product? It increased, exactly. Another 5 seconds, another 5 seconds, okay. I think that's it. So yeah, you see the molar concentration of the reactant decreasing, molar concentration of the product increasing. Makes sense? Okay. Now, actually, you're going to have to wait till Friday before we kind of talk about this K. Way too many Ks. If I could go back in time and say, dude, can you make like a constant something else, because we have KHs, and oh my gosh, there's actually 2 more Ks coming up. This actually is the rate law constant. Ugh, you serious? We'll be talking more about that on Friday. Okay. So this actually is plotting those 2 things. Let's see, the red, you think that's reactant or product?
Reactant.
It is reactant. Why? Because the key says it, but.
Because it's going down because time's going on. And
Exactly. The red is the reactant, and if you're kind of colorblind, that's the circles. Yep. And we see the green is the product increasing. Okay. It's not linear. We kind of have some sort of exponential thing going on there. I think if I had to put a curve fit to it. Right. Well, okay. So how fast is it occurring? I'll put this up on the board. Reaction rate, RXN, stands for reaction rate, is equal to, what's delta mean? Change in, yep. Change in molar concentration of either the reactant or the product. I'll just go ahead and put reactant over change in time. That's it. Well, let's see. I'll say reaction rate. I guess I'll leave it that. I'll have to come revisit that here in a minute. Reaction rate is equal to change in molar concentration of the product, change in time. Now I'll have to revisit that, like I said, because reaction rates are always positive. So on this scale, we have molar concentration of reactant and product on the y-axis, and we have time on the x-axis, right? So change in molar concentration of change in time, that actually is represented like here. Change in reaction, change in time. Change in molar concentration, change in time. Now that blue line, it would just be from what segment? If these look like they're each 2 seconds, right? 2, 4, 6, 8, 10. So that would be for the first 2 seconds. That look right? Okay, so the slope, that was my point here. How slopey that line is, oh, that's a burr, or this, yeah, is actually the rate at that time. So let's go ahead and we're going to go down the road. This looks like what, 2 to 4 seconds? Wait, 4 to 6 seconds. Final answer. Does that look right? Okay. 10 to 12. 18 to 20. Now, if you were to kind of compare that, what's happening to the slope? Is it getting greater or less? Less. The slope is decreasing, exactly. So, the rate is decreasing. That's all it is. So we could go from, take a quick look at from 0 to 10 seconds. That would be the slope of our line. But if you want to get down to the nitty-gritty, maybe you guys already know this and I'm not as up into math as I should be. If you want to know the slope at any point, what you do is you take a line tangent, you draw a line tangent to the curve at that point. that looks like this. This is a line tangent to the curve at, we'll go with 10 seconds. You guys buy that? Okay. So that would be a true snapshot. And I'm not going to make you draw any tangent lines, but that's what we're talking about here. A snapshot of the rate at 10 seconds. So as we get going, actually, and I don't know if you'll find this helpful, there's something when we talk about reaction rates, there's initial reaction rate. And that's a lot of times what we care about, that initial reaction rate. We don't care about down the road, 20, 30 seconds. All right. So rates, we can follow the change in molar concentration of the reactant as it decreases, sorry. As the reactant decreases, or change in molar concentration of the product as it increases. We can do whatever we need to do. So we're going to look at that data. If you put a star, we're going to be looking back at that data. Basically, you take 2 times, and time 2 is usually later than time 1. Okay, so you take the molar concentration at time 2 minus the molar concentration at time 1, and then you take the difference in the times. Okay. Now, for a reactant, you buy this, that the reactant in time 2 will be less than the reactant in time 1. So these are going to be negative. It's true. So for the product, we take the molar concentration at time 2 minus the molar concentration at time 1, and we divide that by the change in time. Not bad. Okay, so again, if you have it, if you start it, go back to it. Go back to that, like our reactant going to form product, and the 5-second intervals. If you look at the first interval, it looks like this then. The change in the molar concentration of the reactant would be R2, 0.121, minus R1, which is 0.200. And again, if you have the same units, in this case we're just subtracting or adding, you can put those units to add or subtract in parentheses, and outside you can put the units. So moles per liter, the units there. Okay, so that gives us a negative 0.079 moles per liter is our delta change in molar concentration of reactant over that first time interval. Our change in time, it's T2 minus T1. T2 is 5 seconds, T1 is 0 seconds. Okay, so your delta T is 5.0 seconds. So then to get the rate over that interval, we just need to take the change in molar concentration of the reactant, that top number, divided by the change in time, that bottom number. So the rate at that point with regard to the reactant is 0.016 moles per liter per second, and of course it's negative. Any questions about that? I got a little sloppy here. Look at this. Look at my delta T. Should be 5.0 to give 2 sig figs. Any questions about that?
So this is similar to the Clausian-Clapeyron slope.
I think so. I think that works, yeah. Clausius-Clapeyron plot. No. The Clausius-Clapeyron plot units were units of inverse Kelvin. Because, yeah, natural log of pressure was unitless. But, yeah. Okay. And I'm not going to do it, okay, but if you go back and look at the column for the product, and you come up with the delta change in molar concentration of the product over that same time interval, you are going to get and divided by the change in time, you're at 5 seconds, you're going to get a positive 0.016 moles per liter per second. Okay. Sometimes, and while I'm thinking of it, so you guys are probably like this. I really think you could do moles per liter per second. I'd be fine with that. It's the same diff. Does that make sense? Moles per liter second. It's the same thing. All right. Now, what did that, with looking at the rate of change of the reactant have in common with this one, looking at the rate of change of the product?
Inverse.
Numbers. Yeah, it's the same number. What's different about it?
Plus the negative.
Plus and the negative, exactly. If you track a reactant, it's always going to be negative. If you track a product, it's always going to be positive. In this case, I think my slides say it, in this case, well, maybe it says it later on, the only reason that they're the same number is because the stoichiometry is a 1-to-1. We're going to actually kind of have to introduce stoichiometry coming up here. But if it is a 1-to-1, that's actually going to be the relationship. All right. So we just came up with these numbers. Yep, we came up with these numbers. If you were to do a similar thing of the next interval from 5 to 10 seconds, what we should see is a few things. One is we should see those rates decreasing. Does it look like it's slowing down? Yeah. And this would be the 10 to 15, and this is the 15 to 20. Okay? Any questions about that? You should be able to kind of come up with these numbers. Just on that page you had a star. So if you're looking for something to practice on, you know, these numbers are available for you. So like I said, the rate of the formation of the product is equal to the rate of the decrease of the reactant, okay, only in this case because the stoichiometry is a 1-to-1. Oops. I think we're okay with that. Okay. So here's where I need to kind of, I kind of call it normalizing. Normalizing means just fixing it so that you can compare apples to apples and oranges to oranges. I don't know where that phrase came from. Okay. But, and this is where I probably kind of need to erase this. Our true reaction rates need to always be positive. So here in a minute, I'm going to introduce this. What's this? It's not like an airplane. What is it? What mathematically is it?
Absolute.
Yes, that's absolute value. I'm going to introduce that, okay? So they always have to be positive.
Colligative property.
Colligative property, that could be too. Okay. And the other thing we need to do is normalize for the stoichiometric coefficient, okay? Don't let that throw us off. So we're going to look at something generic. We have some more interesting stoichiometry going here. We have a coefficient of 2 in front of the reactant, the A, and we have a coefficient of 2 in front of the B, and the other product that's formed is C, and there's a coefficient of 1. And so you would imagine that if you track the consumption of A, does this make sense? If you can track that, that should be twice as much as the production of C. I think so. Yeah. And so if you track A or C, an absolute value is not going to do it for you. You have the plus or minus thing, but you also have to normalize for this too, okay? Which isn't too bad. I'll show you how that works. All right. So let's just say, and what does that, you guys told me brackets mean molar concentration, and then what does this little 0 mean down here?
Is that initial?
It is initial, exactly. That's initial at time 0. So at time 0, the molar concentration of your reactant A is 0.100 molar. You let it go for 25 seconds and it's decreased to 0.060 moles per liter. Okay, very good. So we're going to kind of think through this. We can come up with the rate of change of the reactant. That'll be just your delta molar concentration of A divided by delta T. Okay, and then we can actually from here figure out the molar constant or the rate of change of C, which should be what, half of A? I think so. All right. So plugging in those numbers for A, you get this. The change in molar concentration of A, it's always final minus initial. So it went down to 0.060, moles per liter, and it started at 0.100 moles per liter. So that's where, of course, we're going to get our negative from the numerator. The time interval is T2 minus T1, 25.0 seconds minus 0.0 seconds, 25.0 seconds. So you need to make sure that when you're working these problems for homework or on your test, you make sure you keep the units with it. That will help you. So our delta molar concentration of A is negative 0.040 moles per liter, or big M. Our delta T is 25.0 seconds. Rounded 2 sig figs, I get negative 0.0016 moles per liter per second is the rate of change tracking A. Change in molar concentration of A over change in time. Okay. Yeah, I'll do it this way. This part kind of, and this will enter in later in the course. So when we have 2A goes to form 2B plus C, right? And we started out at, I'll put 0 and 25. I'll put time here in seconds. 0.100 moles per liter, 0.060 moles per liter. Okay, so based upon stoichiometry, the next few slides are going to kind of talk you through this. You need to be able to use this decrease. What is the amount that was converted here? You guys buy that? So this is the amount that went over there. Does that make sense? Because that's the amount you have left. Okay? If that's the amount that was converted to both of these products, okay, what's the molar concentration of this guy over here? Make sense? You buy that? I'm just eyeballing it. Right. So in order to get I did that because we're going to look for, basically, we need to come up with a rate of change of C over time. That's what we're after. So what was C at time 0? 0. It was 0. Can you come up with a delta there? Yeah, I think so too. Okay, so do you see where this 0.040 moles per liter of A came from? Again, I've never done this, but I just think it's a visual thing. Where did it come from? Well, we started with 0.100 molar. We, at 25 seconds in, which is the interval of interest, we were at 0.040 moles per liter. So we reacted 0.040 moles per liter. We can introduce a stoichiometric coefficient. Okay, it looks like this. 1 mole of C over 2 moles of A. And of course, when we do that, we're going to get the 0.020 moles per liter that you maybe kind of intuitively thought. Okay? So now we're that close to coming up with the rate of change of C over that time interval. Because you guys told me it was 0, molar concentration 0 at 0. Okay, so it's always final minus initial. Now here's where I think got a little sloppy again in my notes. I really think that numerator should have said quantity 0 moles per liter. Wait, sorry. It's final minus initial. Quantity 0.020 minus 0.000 moles per liter. Okay, are we good with that? Okay, sorry about that. time interval 25 seconds, rounded to two significant figures, you got the rate of change over that same time interval is 0.00080. That's a lot of zeros. All right, if you go back a few slides, we knocked out the rate of change of A over time, 0.0016 moles per liter per second. Same time interval. Does that make sense? That this is actually twice of that. Okay, good. If you compare those two, here they are side by side. Now you guys told me that those are the absolute value of, okay? So already we're kind of removing the negative associated with tracking the change in a reactant. But we still got an issue going on. Reaction rates need to be positive, okay? The other thing about the true reaction rate of a reaction is it needs to take into consideration the stoichiometry. So we need to basically fix our A because that is a stoichiometric coefficient of 2. So these are right, okay, following the rate of change of A is that. But if you were going to say what the real reaction rate is, you have to, down here in blue, the second one, the effective stoichiometry is removed by dividing by the stoichiometric coefficient of that species. So it looks something like this. These are great. These are valid. Okay. But if I was going to say the true rate of this reaction, the rate, I'll say reaction rate. And if I wanted to use my following the molar concentration of something that has stoichiometric coefficient of 2, I would have to divide by the stoichiometric coefficient okay? All right, that's it.
Can you go back for just 1 second, please?
I can't.
That's all I need, thank you.
And I think this is kind of funky how my slides do this too. Instead of like the absolute value, the reason I've introduced a negative up there is because I know it's a reactant and going to decrease, so it's a negative, and so in order to make it a positive, I introduce a negative, which is, I think, kind of dumb. I'd like the absolute value thing better. Okay? And notice then we could actually, we didn't, but we could do a similar exercise tracking the change in concentration of the other product, B, and if we did that, we would have to take that rate of change times 1/2 also because it's got a coefficient of 2 in front of it. The only one that you don't have to monkey much with is if you track the rate of change of something with a coefficient of 1, stoichiometric coefficient of 1, and it's a product, okay, which is C. So, in other words, this right here, this is the reported reaction rate. Dun, dun, dun. All right. So what do we say the reaction rate for this is over that time interval? Now remember, reaction rates slow down over time. It'd be faster earlier on in the life of the reaction. We say the reaction rate is 0.0080 moles per liter per second. Because of course if we take, oh, did I should do, sorry. Okay. All right. And for this homework is gonna, this is actually, if you go down to the last slide, we'll kind of take a look at these, but this will be due on Friday. And this is actually the last slide in this part. We are still gonna do those, the next part too. And I don't know if you guys all heard me, but the reason we're kind of rushing into this is you need to have something that makes sense for tomorrow's lab. So it'll make even more sense. Oh, yeah. Well, I was going to tell you in pre-lab, but I'll tell you now. So this is my husband's idea, which I'm like, wow, you thought of the idea? And anyway, he's like, well, since you're kind of, tomorrow's lab, the calculations won't make as much sense as they will after Friday's lecture. So it's like, you know what you should do is just go ahead and tell them that they don't have to do a full-blown write-up. They just have to do the calculations. I know. I'm like, really? That sounds like something I would come up with. So I think that's what we'll do. So tomorrow we'll do pre-lab and everything, and we'll talk about the calculations, but it'd be like, they won't make sense until really Friday. And then don't worry about a full-blown report.
Just
But-
do the calculation.
Yeah, do the calculations on time. So yeah, how fun is that? Well, let's take a look at what these look like. They look like. Dun, 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 dun. Okay. Another thing about Unit 2, well, not another thing, but something about Unit 2 is when I look at, in the past, the number of assignments for Unit 2, the unit is shorter, but there's fewer assignments. So that's kind of fun. For me too, I don't have to grade as much, but the unit is shorter than Unit 1. So this one has, you see the stoichiometry of the reaction in the top there. And let's see what it gives us. Reactant A is found to disappear at a rate of 6.2 times 10 to the minus 4th moles per liter per second. Okay. A, what is the rate of the reaction at this point? So basically, what they're giving you is this. They're giving you this, and you need to normalize it to what the real rate is. Okay, so it's going to be the absolute value of, okay, so it's not going to be, well, there's not a negative there, but there would be a negative there. Absolute value, and then what are you going to have to multiply it, or, yeah, multiply it by? 1/2. That's it. I mean, I hate to say how to do it, but that's exactly it. You got it. What else do I have for hints here? The next one, what is the rate of appearance of B? Okay. Oops, sorry. Now, what I would do is I would go back to this kind of thing, the original information, and I would, kind of like we did in lecture, I would introduce, this is my stoichiometric ratio, okay? So I want moles of A to cancel, I want to be left with moles of B. This sounds like Chem 1. So what numbers go there?
1 mole of B, 2 moles of A.
Yeah. So if you take that ratio and insert it here, you're going to get from moles of A to moles of B. Okay? But B is kind of like the same thing as the reaction rate, except for it being negative, because it's got a coefficient of 1. The next one, rate of formation of D. Okay? Okay. Now this one, looks like you're dealing with this figure. This is the decomposition of hydrogen peroxide to form water and oxygen. So you kind of see some black line and a blue line there. But if you go back to the question, it's if you pick on time is equal to 800 seconds, okay, they want to know what is the rate there. Like, I don't know. My hint was, you know, this is kind of broad. My hint was, well, smack dab 800 is between 400 and 1200. Okay, I would go ahead, go up, see what the molar concentration is at those times to get my delta, my change in molar concentration, and then my time. If I go that route, my delta T is going to be what, 800 seconds? Okay, so that's one way to do it. Or draw a line tangent and try to get the slope of that. But I think that one would be less mind-boggling. And then the next one says, excuse me, Next one says, what is the time when the hydrogen peroxide molar concentration is down to 0.50? So you see the H2O2 decreasing. So you find 0.50 and you pick off the time. I mean, I don't mean to do your homework, but that was not too bad either, okay? So, okay. Next one. They say so A goes to form products. It goes ahead and says that molar concentration of A will decrease from 0.485 to 0.474 over that time interval. Okay, well, you guys can do this. Yeah, you're fine with that. All right, this one. It gives you the initial molar concentration of A. It says after a minute, it's going to decrease to what you see there. After 2 minutes, it's going to decrease to that other one. Calculate the average rate during the first minute and during the second minute. So A actually has two parts to it. Why are they not equal? Well, hopefully it's going to decrease, and reaction rates always decrease over time. Was that it? Is there one more?
There's, I think, 7 is the last one.
Okay, thanks.
Yep.
Okay. Okay, a little bit of stoichiometry given there. It gives the reaction rate. Let's see. Formation of C. So this one's kind of like what we did over here. Okay? Wait. It gives you the reaction rate. Oh, okay. So the first one, you just need to see where I have stoichiometric coefficient. That's kind of like this. That's the ratio. Okay, to get from the change in molar concentration of A, change in molar concentration of C. For B, well, here's where I would use that molar concentration change in A per second as basically a conversion factor. Okay, so my first term is going to be the 60 minutes. I'm going to have to convert minutes to seconds. And then if I insert this, I can get the what the change will be by just applying a rate. So that was my hint there. Assume that it rate remains constant, which we know will decrease. How long would it take for A to change from the original to 0.3500 moles per liter? Again, use the rate as a conversion factor. So come up with what your change is. Oops. Come up with your change and basically multiply it by the rate. And that will give you the seconds in order to get to that. Okay. Very good. You know, I'm not sure I got my videos working here, but we can at least do a little bit of this, okay? So, reaction rates. How long does it take? And we're going to be actually, I don't necessarily put a star by it, but we're going to be talking about these factors in how fast a reaction occurs or how slowly a reaction occurs. It's kind of fun. First off, the particles need to collide. Now, this is assuming that you have like two reactants that need to find each other to go to form products. Okay? Life's about chances. They need to collide. The other thing is, even once they do collide, they need to have enough energy to go sometime. Well, yes, there's always an energy barrier. And we're going to be looking at energy diagrams of chemical reactions occurring, but they basically need to have enough energy to proceed to form products. To find each other, have enough energy. And then last but not least, oftentimes there is an orientation issue. We're going to talk more about this, but if you're familiar with a catalyst in chemical terms basically helps the orientation go along. They're just kind of providing a platform so they can find each other and be properly oriented. So if you look at this, reaction rates, it's to me, it's mind-boggling that any reaction occurs. Particles find each other, they need to have enough energy, and they need to be oriented properly. And I don't think these videos are going to work for me. Okay. Well, that's where I need to stop because I don't have my videos working. So,
Excellent.
we'll top off this part on Friday and then start in on part 2.
Okay. But we have enough that tomorrow will make sense?
I think so.